Okay, so we're going to look at some calculus of variations today, and this is multivariable calculus, not like single variable calculus that you would have done in first and second and third years. So we've got the notation here. So our functional of y with a boundary of 0 and pi over 2 is integrated with regards to x, 2y squared minus y prime squared. Now this bit here, this is our functional, which I've got here. Now y is a function of x, y prime is also a function of x, and we've got x, which is our dependent variable. So what we need to do to find the Gateaux differential, we've got this formula here which I've written down, which looks quite intimidating, but when you go through it, it's doable. So we've got the Gateaux differential is derivative with regards to epsilon of s y plus epsilon h. So we need to introduce an epsilon h in here. We'll go through that in a minute. And then we take the limit as epsilon approaches 0. Now, first of all, we need to change the notation in this functional here. So let's first of all begin with this part. So s of y plus epsilon h, that equals, so the boundary conditions stay as they are, and it's always regards to x. And what we do here now, wherever we see a y or a y prime, we introduce an epsilon h prime or epsilon h regards to whether it's a y or a y prime. Okay, so let's first of all go into that. So keep the bracket there. So we've got 2 y plus epsilon h, and then that will all be squared. So that fits the conditions here. And now we're going to subtract y prime squared. So now we'll have a y prime minus epsilon h prime squared. So that's the first stage into the Gateaux differential. Now what we see here, h here is also a function which is important for admissible paths, which I'm going to go into in another video. Check the link down below and I'll show you what that's all about. But next stage, we need to take the derivative with regards to epsilon. So then we'll take the limit as epsilon approaches 0. So first of all, let's introduce this derivative here. So let's put the derivative with regards to epsilon of s y plus epsilon h equals, now epsilon is independent of x, so we can bring this derivative inside the integral. So 0 pi over 2 dx, and then we take the derivative with regards to epsilon. So let's do that in here. So first of all, let's deal with this term. Now we can use the chain rule here, bring the 2 out front, reduce that by 1, and then take the derivative with regards to epsilon in what's inside the bracket. So that will then give us 4, bringing the 2 out here, and then y plus epsilon h, that won't change, and then the derivative of epsilon h with regards to epsilon, it's just h. Okay, so now let's deal with this one. So very similar as before, except we're now dealing with a y prime, but don't let that intimidate you. So bring the 2 out front, the y prime minus epsilon h prime, and then the derivative of epsilon h prime, which is just h prime. Okay, so now what we need to do now is take the limit as epsilon approaches 0, which is just basically plugging in 0 for epsilon. So now what we end up with is from 0 to pi over 2. So write this down as d epsilon s y plus epsilon h, all as epsilon approaches 0. So let's go through this carefully. So this is not affected. So if this is 0, this is cancelled out. So that equals 0. And then in here, this is not affected, this is not affected, obviously this is not affected, but this also will become 0. So now we can just write it now without these terms. So now we've got dx 4 times y times h, and then this one minus 2y prime h prime. Okay, so what we're left with now is perhaps we could bring a 2 out front, so we can just finish off our Gateaux differential now. S y comma h, that's our Gateaux differential, 0 to pi over 2 dx, and then we've got, bring a 2 out of here, so we've got 2, and then here we'll have 2yh minus y prime h prime. Okay, and that is a good place to end.